Hi, I'm Eyal. I'm a student of Diller, and I want to tell you about our joint work with Bairey on reconstructing quantum dynamics from their steady states. So suppose you're an experimentalist, and let's start with some motivation. Suppose you're an experimentalist and you want to implement some quantum circuit in your lab. So ideally, it would look something like this, but in practice, your system is noisy. There are some, there are some stray fields and couplings affecting your qubits, and they're acting on your system at all times, even when you're not applying any gate. So in practice, it would look more like this. So there's some nasty, unknown Hamiltonian that's acting on your system at all times. And you want to characterize this noise. You want to learn this Hamiltonian so you can tune your experimental knobs to suppress the noise. How can you do that? So one approach would be to initialize the system in some fixed state, and then let it evolve for some time under this, for a short time under this nasty Hamiltonian, and measure it. You can then compare the measurement statistics to the initial state and try to see how these dynamics change the state. But there's another approach. We can start the system, we can initialize our system, then go make some coffee, come back after a while, and measure it. So while we were drinking,
the coffee was the difference.
Yeah, the coffee was the difference. While you were drinking your coffee,
Let's talk about vodka.
you can also go to a pub, give you more time. While you were drinking your coffee or your vodka, the system had time to equilibrate to a steady state.
So it's the length of the time.
Yeah. So this is short time dynamics, and this is long time dynamics. And
Steady state.
it reaches a steady state of the Hamiltonian, and then you can try to extract information about this Hamiltonian by measuring this steady state. So at first glance, this second approach might seem hopeless because this steady state is highly entangled with correlations spread throughout the system. How can we measure this steady state to extract the Hamiltonian? So what do I mean by a steady state? So for a time-independent Hamiltonian, a steady state would be any state that commutes with the Hamiltonian, right? Because then it doesn't evolve in time. So it can be an eigenstate. It can be a Gibbs state, also known as a thermal state. And actually, any state evolved for sufficiently long times approaches a steady state as long as you measure it at some random time. So condensed matter physicists are obsessed with these steady states. We write down Hamiltonians, and then we use supercomputers to solve them to get their steady states. But it's not always clear which Hamiltonian we should write down. What are the couplings in the Hamiltonian, what their coefficients should be. So here's another motivation. Suppose you have some material in your lab that's in a steady state. How can you derive that? How can you infer the Hamiltonian of this material by measuring its steady state? So we know that this problem is exponentially hard. We use supercomputers to solve it. What about this inverse problem of extracting a Hamiltonian from its steady state? Is this problem also hard? Actually, is it even well-defined? Does any state have a unique parent Hamiltonian? Well, obviously not, because if you start from any given state psi, you can always write down a Hamiltonian which has psi as its eigenstate. Well, a whole family of such Hamiltonians. You just write, a projection on this state, and then anything that acts on the orthogonal subspace. So this whole family of Hamiltonians has psi as its eigenstate. So what's the catch? The catch is that if your steady state if your eigenstate is entangled, then this projection is a very non-local operator. So this family of funny Hamiltonians would be very non-local. Physical Hamiltonians, on the other hand, are local. So they're given by a sum of terms that each acts on just a few neighboring sites. For example, a Hamiltonian on a two-dimensional lattice with nearest neighbor interactions. So here, these are operators acting on single sites and nearest neighbors. Now, the family of local Hamiltonians is actually quite small. There aren't that many local Hamiltonians you can write down. The space of local Hamiltonians grows only polynomially with the number of qubits. On the other hand, the space of all quantum states is huge. It grows exponentially with the number of qubits. So if you're lucky enough to encounter a steady state of a local Hamiltonian inside this huge Hilbert space, you don't expect it to be a steady state of another local Hamiltonian. And the remarkable fact that I want you to take from this talk is that given a certain state, a simple set of measurements can distinguish whether this state belongs to this special family of steady states of local Hamiltonians, or maybe it is far away from being the steady state of any local Hamiltonian. Okay. So specifically, we propose an algorithm for recovering the Hamiltonian from a variety of steady states, eigenstate, Gibbs states, long-time dynamics. Our algorithm uses only local measurements, so it allows to extract the Hamiltonian acting on a spatial patch using only measurements within that patch. And finally, it's efficient in terms of number of measurements and computation time. So what's the idea? Suppose we have some state that is steady state, doesn't evolve under the Hamiltonian. The key to extracting the Hamiltonian is using Ehrenfest's theorem. Ehrenfest tells us that since we're in a steady state, well, we know that since we're in a steady state, the expectation value of any operator must be time independent. So Ehrenfest tells us that the expectation value of the commutator of the Hamiltonian with this operator must vanish. And this gives us some constraint on the Hamiltonian, assuming that we can measure the steady state. So this constraint is purely local because, well, if we pick an operator A that lives on these three sites, then the commutator of A with the Hamiltonian will only involve Hamiltonian terms that act on the same sites. So this gives us a constraint on the Hamiltonian terms that act on the same sites as A does. How can we use these constraints to extract the Hamiltonian? Well, we can expand the Hamiltonian in some basis of local operators. So we assume that we know the basic building blocks of the Hamiltonian. These can be all operators acting on single sites or nearest neighbors. We expand the Hamiltonian in this basis of local operators, and then this constraint becomes a linear constraint on the coefficients of the Hamiltonian in this basis of local operators. So what does this constraint mean? Well, this commutator tells us how the expectation value of the observable A would change due to the addition of this Hamiltonian term, and we demand that the total change in the expectation value of this operator vanishes. So this is one constraint on the Hamiltonian, but one constraint is not enough. However, we can repeat this process for different observables and gather many constraints. And if we gather enough constraints on the Hamiltonian, we have some hope to recover it. So we use many constraints. Each constraint gives us a linear equation. We stack these linear equations into a matrix where each row corresponds to a constraint operator, and each column corresponds to one of the possible Hamiltonian building blocks. The true Hamiltonian must solve all these constraints. It must obey all the constraints. So it lies in the kernel of this matrix.
The index M is running around around the pink point. The index M.
The index M is the index of the Hamiltonian terms. So it runs over all the possible Hamiltonian terms.
So there has to be another index of where are you doing the measurement? No.
The index M is only over the operator.
Okay, so there are two indices.
To only few. M is limited to only few neighbors.
No. Okay. Right now, I'm looking at the whole system, and soon I'll explain why this algorithm can be applied to a subsystem embedded in a larger system. So now let's consider this whole system, and the index M runs over this whole system. So the index M corresponds to these blue terms, the terms in the Hamiltonian, and the index N is the index of the constraint operators. Okay, so we have many linear constraints in the Hamiltonian. So this gives us an algorithm for recovering the Hamiltonian. We expand the Hamiltonian in a basis of local operators. We measure these commutators, put them into a big matrix, and solve the linear equation. Well,
can you give me an example for a local operator that forms a Hamiltonian?
Yeah, like sigma z on site 17.
Okay, so you're talking about spins.
Spins, yeah. But it can be extended also to fermions or whatever. So we measure this matrix of commutators. We solve a linear equation. Well, in practice, we cannot measure these commutators to an arbitrary accuracy. So our equation won't have an exact solution. So instead, we look for the Hamiltonian which violates the least constraints. That's the lowest eigenvector of this matrix. And this is our guess for the Hamiltonian. We can actually evaluate how good is this guess by looking at the spectral gap of this matrix. So using a simple perturbation theory, we see that the spectral gap of this matrix dominates the reconstruction error, or how hard it is to distinguish between the true Hamiltonian and any false solutions. So we measure the reconstruction error by the Euclidean distance between the normalized coefficients of the recovered Hamiltonian and the true Hamiltonian. And for a fixed gap of this matrix, for a fixed level of noise, a larger gap means a smaller reconstruction error.
How do you measure the spectral gap?
Okay, I get a matrix of commutators.
For the eigenvalues?
Yeah.
So that's the spectral. Where is the gap?
So if I measure this matrix to arbitrary accuracy, it would always have a solution. It would always have a zero eigenvalue. And then the first excited.
Eigenvalue is due to the fact that you're measuring an steady state.
Yeah, exactly. And then the first excited eigenvalue will tell me how hard it is to distinguish the true Hamiltonian from a false solution. So that tells you the robustness of the recovery to noise. Did I answer your question?
No, I don't understand. How do you know how do you determine a false solution?
How do I determine a false solution?
What is a false solution?
What?
How do you know this gap from a false solution? What is a false solution?
A false solution is not the right Hamiltonian. It's a Hamiltonian which is not is a different Hamiltonian than the Hamiltonian for which the state I'm measuring is really a steady state.
You have infinite wrong Hamiltonians. So
Well,
talking about the closest one or something.
Okay, so
he's only working with K and N. That's all he has in his hand. K and N. Work with K and N. Am I right?
okay, so
you measured.
I have a matrix, and the different eigenvectors of this matrix are different Hamiltonians. So I look at the lowest eigenvector, it tells me the correct Hamiltonian, and then the next one is a false Hamiltonian. That's misleading me. Yeah. So let's see experiments, how it works in practice. Oh, and just before that, I'll answer Amit's question. Well, suppose we want to apply this algorithm on some system that's embedded in a larger system. Well, as long as we only use constraints that live inside the system, our equations will only involve Hamiltonian terms that act on this subsystem. So that's why this algorithm is really local. So okay, so it sounds good, but does it work? Let's see. Okay, and maybe this will help understand what I mean by the error in the reconstruction. So we did some numerical simulations. We generated random Hamiltonians. So we took all possible terms acting on single sites and on nearest neighbors. Then we extracted so we draw the coefficients of these terms from a Gaussian distribution, just to look at generic Hamiltonians. We then obtained the ground states of these Hamiltonians, and then we attempted to recover the Hamiltonian from these ground states using an increasing number of constraints, starting from single site constraints, constraint acting on 2 consecutive sites, 3 and 4. And we add a small error to each of the measured observables to mimic a realistic setting.
Where is damping in this model?
Okay, so here there's no damping yet, but I'll introduce it later. And we see that as soon as the number of constraints reaches the number of unknowns, the number of terms in the Hamiltonian, this error drops, which means that we recover the Hamiltonian, and the accuracy to which we recover the Hamiltonian increases as we add more and more constraints.
The constraints are the commutators that you're measuring?
So the constraints, okay, so the constraints are the operators for which I'm demanding that the expectation value doesn't change in time. Each constraint gives me a few observables I need to measure. Okay, so we see that it works for ground states. We can recover the Hamiltonian from its ground state. Actually, the accuracy to which we recover the Hamiltonian is only limited by the measurement noise. If we decrease the measurement noise, we will recover the Hamiltonian to an arbitrary accuracy. So this is for ground states. We can also repeat this for thermal states, for the Gibbs states of these Hamiltonians. For thermal states, we see that as temperature increases, the reconstruction error increases as well. Well, this shouldn't be too surprising because as temperature increases, the state becomes less informative. It approaches a fully mixed state, which is compatible with any Hamiltonian. We can also do some dynamics. As I mentioned before, if we take time average dynamics over long times, then the state approaches a steady state. And here we see that if we attempt to recover the Hamiltonian from this time average state, then it approaches a steady state as time increases, and we recover the Hamiltonian to a greater and greater accuracy. And we can even extend this to time oscillating dynamics and recover both the time independent component of the Hamiltonian and its time oscillating component.
What's the time? Seconds, hours, days?
It's okay. The time is measured in units of the Copley constant. Okay, and finally,
You were talking about steady state. So what's the time here? I don't understand.
okay, so I take a fixed initial state, like a product state, and I evolve it in time.
Okay.
And I take a time average, which means it's equivalent to just measuring the state at some random time between 0 and t. And the statement is that this thing approaches a steady state as time goes on.
Okay.
And we see that it approaches a steady state better and better because by measuring this time average state, we recover the Hamiltonian to a greater accuracy with time.
Okay. And in the previous one, when you introduced temperature, it was just Boltzmann
A
distribution? Or something?
Gibbs state, yeah, exactly.
You need to know the initial state.
So in this case, you don't really need to know the initial state. Because for any initial state you start in, it will equilibrate to a steady state. But there is some caveat here if you want, I can tell you later. Because if it equilibrates to a fully mixed state, then you get no information. So you should start with a low energy state. Okay, so then Eyal asked about dissipation. So in fact, we can extend this to systems that are evolving under non-unitary dynamics. So if you have a system that's weakly coupled to a large environment, then in some cases you can approximate the evolution of the system alone using an effective equation known as the Lindblad equation. So in addition to the coherent terms in the evolution, there's also these dissipative terms. And then the Heisenberg equation or the Ehrenfest equation gets this dissipative term. We can extend our formulas into this setting, and indeed we find that if we measure the steady states of these systems, and I should mention that in contrast to Hamiltonians, which have many eigenstates, a generic Lindblad evolution reaches a unique steady state, which depends on the dynamics but not on the initial condition. So surprisingly, the steady states of these Lindblad evolutions, but by measuring them, we can extract both the Hamiltonian dynamics and the dissipation that affected the system like before it reached its steady state. So the steady state really contains the information about the previous evolution. And so here again, when the number of constraints reached the number of unknowns, the error dropped, and we can even incorporate prior knowledge. So if we know the Hamiltonian and we just don't know the dissipators, then we can recover the dissipators to a higher accuracy using fewer constraints. That's it. So we're currently working to extend this to to some challenging settings that arise in realistic quantum devices, like power law decaying interactions and commuting Hamiltonians, which correspond to topological error correcting codes. Thank you very much.